Welcome to CS1104. This is Computer Systems. This is the Unit 3 lecture, Part 1. And during this lecture, we're going to look at combinational logic circuits in a little bit more detail. So the previous unit, we were looking at some combinational logic circuits, and in particular, we were looking at things such as the half adder and the full adder. We briefly covered the idea of a multiplexer, demultiplexer, and we talked about all of these things are brought together to form the basis of the ALU, and the fact that the ALU is the central core of what actually does computation in a computer system. So we want to kind of go back, and this is going to be somewhat of a review, but really kind of talk about combinational circuits and kind of define them for you, because we just gave you an example before. I want to just kind of define it, but a combinational circuit is something that consists of logic gates whose outputs are at any time are determined by combining the values of the inputs. Now, what's really unique about combinational circuits is that they are different from sequential circuits. So combinational circuits means I put a bunch of gates together and they produce some result. So I have some result that's output from the inputs. And so for any n input variables, I will have some 2 to the n possible binary input combinations. And so again, combinational circuits always have a series of inputs and we have a series of outputs, and those inputs and outputs can be defined by a truth table, and they produce a value, right? And that value is not persistent. It doesn't have any kind of preserved state. When I put the inputs in, it produces the outputs. And so I've got kind of this whole model of I put the inputs in on the one side in my combinational circuit, and I get those outputs out. And we're going to see this a little different than what we would find in sequential circuits, because in a sequential circuit, essentially what I'm doing is I'm holding state. I have this idea of feedback. So not only am I putting a value in, but I'm holding on to that value somehow. I'm actually going to continue to keep that circuit alive long after perhaps I stopped providing the inputs, such that the output is preserved. And if you think about it, this idea of preserving state is what memory is all about. So when we start looking at sequential circuits, the one of the primary uses of them is in creating circuits that are going to hold something that in memory. So we're going to look at the fact that registers and RAM are actually created with sequential circuits. Now, the sequential circuits themselves are actually built up out of combinational logic, right? It's just some of the ways that we actually deal with the outputs, and we use those outputs as inputs back into the circuit, creating, if you would, a feedback loop that kind of makes them a little bit different. So again, gives you a great view of that is this idea of a combinational circuit. I have inputs on one side, I have outputs. It's real time and state is not preserved. So when I put the input in here, the output comes out here. But the moment I take the input away, the circuit is no longer going to produce any output. Sequential circuits, on the other hand, are a little different, because what happens is I have some input that I'm providing in, and that input is going to go to setting the state. It's actually going to start preserving that. And the way that it's going to preserve it is it's going to keep the circuit alive by providing this kind of feedback loop, right? And so I actually kind of preserve the value. And what this means is I now have to do things like try to figure out, well, at what point in time do I not want to preserve the value? So I have to have ways of interrupting this circuit that we're going to kind of look at. And we'll look at that in a little bit more detail in the next unit when we look at different kinds of sequential circuits. Now, getting back to combinational circuits, one of the things we talked about before was, the fact that we have things like the elements of the ALU, which is the ability to do bitwise and OR, the ability to do an add and subtract. All of those are combinational logic circuits. We also talked a little bit about multiplexers and demultiplexers. What I want to make you aware of is something called a decoder. And so decoders are often referred to as, and even described as, N to M. And what this basically is referring to is it refers to the number of outputs that may be active as a function of the number of outputs that there are. So what a decoder is attempting to do is that it takes some series of inputs and it actually will compute an output. And that output may have one or more different combinations. So, when I see in a typical combinational circuit, I have one input or multiple inputs coming in, and I have one thing that I want to have coming out, or I have a bunch of things coming in, out, and then I want to have one thing that's coming out of that. So essentially, it's kind of the many to one operation. Decoders tend to be many to many. And so this gives you a great view of a decoder and a truth table around a decoder. And here we see kind of we have three inputs, Z, Y, and X. And the combination of these inputs may produce some flavor of outputs. In this particular case, as we can see represented by the ones that are going down the line here, an input combination here only results in one output, which is one way of implementing it. Okay, but I could also implement it in a different way. So I might have multiple inputs that produce multiple outputs. And where we're going to see this idea of a decoder used is oftentimes when we start looking at micro instructions or the circuitry that we actually use to tell the ALU what functions to compute. A lot of times that's going to be represented as a binary number, and I might want to take that binary number and all the inputs of that binary number and produce a number of outputs that allow me to turn on or off some of the features that might be executed within the ALU. Demultiplexer, we kind of talked about this before a little bit. A great way of looking at this is just imagine that I have some series of outputs, and think of it as this kind of this long switch, if you would, right? It can slide back and forth to any of these things, right? So in the demultiplexer, maybe I have some of my inputs coming in here on D0, and based upon these select bits, it's going to determine where this switch is going to stop. So if it stops here, it's going to be selecting the D0. If it stops here, it's going to select D1. If it stops here, it's going to select D2, and if it stops here, it's going to select D3. And the way that I'm selecting these is through the combination of A and B. Now, by the way, we can see there's 1, 2, 3, 4 here, so that means I'm going to need up to 2 select bits, because essentially when you think about the truth table on this, I could have a 0, 0, I can have a 0, 1, I can have a 1, 0, and I can have a 1, 1. Those are the 4 possible combinations, which means I can select one of these 4 using these select bits. Now keep in mind, every time I refer to as 0 means no voltage. Every time I refer to 1, it means that there is a voltage. So basically all we're doing here is we're saying if I have a voltage coming in here, it's turning on one of the transistors. Or if I have no voltage coming in here, it's not turning that transistor on. And again, that's how these circuits are actually functioning. Multiplexer is the exact opposite of the demultiplexer. So where I have many outputs coming into the demultiplexer with one coming out, and the multiplexer I have one input coming in, and then I may have multiple outputs coming out. This gives us a great example of a 2-to-1 line multiplexer. And another multiplexer. In this particular case, we can see there's select bits up here. Here are all my inputs coming in, and this is the one output that I'm going to select.